Oh, well then.
Sergey,
Oh,
welcome.
hello. Thank you. It's great to be here. This will be a short talk, and we're going to talk about things that already happened and that we didn't do, but we could possibly have prevented. This is called the talk is called "For Want of a Nail," and you know, there is this old poem: "For want of a nail, the shoe was lost. For want of a shoe, the horse was lost. And for want of a horse, the rider was lost." And then, of course, there are variants when the battle is lost and the kingdom is lost. We can put it formally like this, right? All righty. Well, but you see, there is something that is gained when a trivial thing is missing in the code, and that thing is usually a pony, right? So for want of that check, a parser is lost and the pony is gained by someone. So in 2013 and 2014, we actually have been plagued by simple and avoidable parser bugs. And all the bugs that I'm going to talk about today were either nominated for a pony or actually won a pony. So there is a certain celebrity factor here. Certainly, you know, it doesn't mean that they are representative, or it doesn't mean that they are the only interesting bugs. But those were the bugs that affected quite a number of people to actually reach that celebrity status. And so we're going to talk about what went wrong, why it went wrong, and how it should be absolutely possible that it would go wrong, in fact, if you look at the code. And that code should not have been trusted in the first place. So what we're dealing with are classes of bugs that have no business existing. And the fact that they plague just about every kind of device we trust is a shame. And of course, we are going to talk about the model for input parsing and validation and processing that should have made this abundantly clear. And of course, you could say, well, hindsight is 2020, right? So yeah, it's obvious to see a bug when the bug is actually found. However, there is another area of human activity where hindsight is important. It's workplace safety rules. Well, we're going to see a few of those posters. Every such rule is written in blood, as usual. And, well, this one says, don't go near the shaft, because that thing on the top would happen. And let's think about our industry, right? That kind of hindsight is seriously overdue. All the more so because in the case of programmer bugs, programmer mistakes, somebody else carries the risk and absorbs the damage. And this is usually the customer, or as the industry calls them, user. And as Felix noted, yeah, there are only two industries that call their customers users. And one of them is drug trade, and the other is software. So we spoke about those things before. We identified this anti-pattern in input handling. We called it shotgun parsers. And it boils down to the validity of field values in the input being checked in every which way, in every old order. And between those checks, you have all the pieces of a Turing-complete machinery such as malloc, memory copy, and arithmetic, and branches and loops. And of course, this is how the code gets exploited, because all those things are privileged. That privilege is given to attackers at the communication boundary, and that's how exploits happened. And we looked at the very famous exploits: bind 8.4, OpenSSH, OpenBSD, pieces of software that were written by dedicated people who thought about security, who cared about security, and nevertheless failed. And the reason why they failed was because the syntax that they were parsing, the syntax of the input that they were handling was just too much to handle, no matter how much you cared. And those were pretty complex bugs, right? So in DNS records, in the NXT records, the famous ADM exploit for that came out in 1999, well, in DNS, names are compressed. So you can't know the length of the host name unless you scan all the way back through all the other records. That makes it context sensitive. And yeah, that was where the buffer overflow crept in. Same with OpenSSH. Multiple length fields of options preceding the option fields that had to sum up across the packet for the packet to be valid. And that was the pre-auth, pre-authentication, challenge response, arbitrary code execution bug exploited by Goebbels. And then OpenBSD had an ICMPv6 bug. Again, you know, you're in the kernel, you can do anything. And that was a fairly complex bug that had to do with how fragment chains aligned with the heap of mbuf packet fragments where the packets were kept. And again, you know, fairly complex bugs, all brought about by there having been too much context sensitivity in the protocol format. So what's new, right? 2013, 2014. I would like to say that those were years of dumb bugs, but you know, again, it's easy to blame the victim, right? The programmer who is made to implement a context-sensitive protocol is the victim and should not be blamed. Well, what's new? Hey, Heartbleed, right? OpenSSL, we trust that thing. Then, of course, OpenSSL again, the go-to-fail Apple bug. Oh, and look, Android is vulnerable too, Android master key. And then even the backbone of internet porn, right, a web server, that was vulnerable. And what really is interesting about all those things is that these bugs are much simpler than the bugs we talked about in 2012. Isn't that interesting? So, simple bugs, common patterns, context-sensitive syntax features, redundant fields which must agree in value across different parts of packets, sometimes across different layers of packets. Dependent values that makes the protocol the format context sensitive. Nested variable length fields. Unless you have to nest your objects, don't. Right? Keep it context free or regular. If you have just a few fields in the protocol, why not have it regular? If you need to nest things to a depth that you don't know, keep it context free. Don't make that context sensitive. In each case, a simple check was missing. And in each case, memory allocation and read or writes happened after the simple check was missing, but was assumed to be there. And so this is the formula for pwnage. Context and ad hoc parsers together make a weird machine, and this is what runs your exploit. Okay, let's look at those in detail. Heartbleed. It's actually a parser bug, right? You have an SSL record, SSL3, and in that record, you have a length field. This is how long the record is. And inside the record is a struct. The struct is identified by its type. That's just 1 byte. And then it contains a length. And then the payload that you want the SSL server to send back to you. And that's your heartbeat. Okay? And so you're thinking, well, there is a length that measures the length of the overall structure, and then the length that measures the length field that measures the length of the payload. What if they don't actually agree, right? Well, that's sort of like your nail, right? Because if you have a large value here and a small value here, which one would be believed? I mean, they should be equal, but will that equality be checked? And it turns out that this value was believed, and this much data was being sent back in the heartbeat message, and that part contained your key and you know, all the other sensitive information. But, you know, digging a little deeper, right, you see that the check that was missing, the nail that was missing, was a check that these two lengths agree. And like, why do you even need that? Why do you even need to have two fields that must be equal for the message to be valid? You're introducing a world of hurt. And of course, this is the parser code that did the check, quote unquote, well, no check. And this is how you did your MMCPY of the code of the heartbeat message going back. And so this shows that there has to be a bright line between where you do your checks, where you do your input validation, where you do your recognition of the protocol. And the harder the protocol, the more work you have to do, the easier it is to make a mistake. And you know, this is where your paranoia is hitting. But then, of course, on the other side, you're sort of playing the trust exercise. You know, you fall back into the waiting hands of the recognition of the recognizer that is supposed to catch you and never, you know, give you up, never let you down. And you can do all of those things confidently, because as a programmer, at some point you have to stop being paranoid and you actually have to write some code. Of course, what happens in reality is this, right? Sanity checks on data are an anti-pattern, and you should run away from it. Input sanitization, the idea that you can somehow recognize badness and that's enough, yeah, again, good luck defending that. And so you look at that code, right? What do you see? This is the parser. This is the recognizer. So yeah, you know, and this is the fix. So you see this code was moved a little bit here, one extra check was added. We're secure now. And, well, are we? So, you know, and then again, here's a special case. And just look at the fix. Look at all that code, right? What are those 1, 2, 16, right? What are all those integers in the code? You know, this is the fixed version. This is the patch. Now, can you actually say anything about the structure of this language that is being received by this code? Is this code any better than the vulnerable version? I say no. I mean, this is the simplest tool ever. The logo reads, "Be careful with a shovel." Right? So, you know, a bunch of integers that have nothing to say about what is expected in the input, so you can't really see whether all the checks have been actually made. And in the end, you know, are you any better than you were before? So, you know, do full recognition before processing. And for goodness sake, make your parser look like the language that you are parsing. Make it possible to glean from the code the structure, the grammatical structure of what you're receiving. And then you can confidently put in this in the comments. You know, and then of course not let the cat down. This was done by Melissa, who works for Veracode and does amazing UTF-8 logos. There's absolutely nothing ASCII about that cat. So go to fail, right? So here is an SSL state machine. Like last time I checked, state machines are drawn with circles and arrows, right? And can be specified in a simple domain-specific language. Now, this is instead what we're getting in Apple SSL library. So, you know, this is check number 1, this is check number 2. So this looks like a linear structure, but oops, what's that? It's probably an extra cut and paste. And if your code looks like this, then yeah, arguably it's very easy to do the cut and paste. So actually the validity check does not happen. You fall through and you're going wrong. This should not have happened. I mean, how easy it is to generate the code for a machine that has a formal description, right? Don't step on fish, right? It's just that easy. All right. Then here's another trusted thing. Android master key bug, and actually Android master key bugs, because there's a whole bunch of them. And you should read Jay Freeman's, blog 17, 18, and 19. You know, he wrote 3 blog posts about the different variants of this bug. But basically, this is how it goes, right? You get an APK, you get your Android package, and then it has to be signed. And you want to check that you are doing it right, that you're receiving a signed, valid package. So, and of course, it's cryptographically signed. And what you should not do with crypto? Write your own, right? So, of course, you're using a Java library for the crypto verifier. You know, hopefully that has been done by people who know what they're doing. One thing, though, this package is zipped. It's a zip zip archive. So you unzip it first, and then you verify it. And then if it, if it fails out, then you discard it and not install it. But if it actually does pass the verification, then you unzip it, and then you install it. And you do that in C++ because, hey, Java is just too painful. And you can do your installation in C++, and that's just great. Except Java has no concept of unsigned integers, and that reflects in the unzipping algorithm, whereas C++ certainly has unsigned integers, and its unzipping algorithm actually uses them. And so what happens is you are getting different contents verified versus installed. So you have 2 recognizers. You have 2 input processors for a context-sensitive language, which is what the zlib library is, right? Can you be sure that those 2 processors actually see the same thing? And the answer is no. It's actually impossible to prove. There is no generic algorithm to do that. Beyond a certain complexity, this just doesn't work. So it was this simple, and it was found because it was this simple. And again, those expositions are just brilliant. But it's actually undecidable to check whether anything beyond deterministic context free is parsed the same way by 2 automata. So good luck testing that, right? It was not fixed right the first time. And Jay had to actually make this argument to Google that no, this is a parser differential. Those things are the very devil to actually fight down. So you have to have the same parser so that you don't have differentials in perception, provably no differentials in perception of your package, right? And it was, in the end, fixed right. But like, again, parser differentials are easy. This says, careful with the pitchfork, right? So how many times do we need to do this? Of course, in 2008, Meredith, 2008, the X509 SSL bugs that 2009, we have already seen that no, you cannot trust different parsers of X509 certificates, SSL, TLS, to parse the same certificate the same way. And we're bitten by this again and again and again. Okay, so let's go to web servers, right? So you have this encoding that is called chunked encoding. And it's simple enough. Basically, if you are going to retrieve a record whose size you don't know, or a bunch of records whose sizes you don't know, you don't have the content length in the headers, but you want to send the headers because you want your response to be snappy. So you're allowed to say that your encoding transfer is chunked, and then your output of the response that you can keep working on after you've sent the headers has the hexadecimal length of the chunk, and then the chunk that is this long, then another hexadecimal length of the chunk, and the chunk that's this long, and then the zero length chunk as the indication that there will be no more chunks. That's simple, right? How easy it is to parse that. So you ask yourself, well, this number, how is this parsed? And people asked themselves that question in 2002. And they asked that question with respect to Apache. And look, it turns out that if you make that number quite big in hexadecimal, then, in fact, if it's an int, well, it could be a signed int, incidentally, which in the code, which will then be taken as a negative number, which then would lead to allocation of not enough memory, which then would be exploitable. And so this is the beginning of that exploit, right? So here is your GET request, and then here is your transfer encoding, and here is your dead beef. Note that this is actually on the request, because you can do that, even though you're typically using that on the response. Okay, so and Apache was found vulnerable and was patched. And by the way, the shell code is then the content of that chunk, right? And this was the fix. Now look at that fix, right? So it was fixed by actually explicitly casting that size that you read to unsigned, which tells you, about the vulnerability. Okay, so, yeah, we know that sort of thing. Watch where you're going, right? And then fast forward 11 years. Now, have people looked at Nginx, which uses the very same encoding, in those 11 years? I would hazard a guess that, yeah, they did. But there is something really special about Nginx, which took, 11 years for exactly the same vulnerability to come to mind, to come to the light. And this was how it got fixed, right? Guess what? If your length is less than 0, then yeah, don't. And this is why it was so hard. This is what Nginx looks like. So we're saying when you parse with a proper state machine. And guess what? Nginx uses a state machine. And it consumes characters one by one, right? So here are your states for the chunk size parsing. And, you can see the integer being accumulated. 0, 9, A to F, this is your hex. And then you change states, and you have this state machine, right? Switching from, chunk in progress to the chunk data to the chunk almost done to the trailer, which is also quite interesting. Ask TQ about that when you have the chance. And then this is the fix, when your state machine is this complicated, and is it so surprising that people forgot to check for this kind of thing? Again, what does this tell you about the language? Nothing much. This is not aggregated. This has nothing to do with the grammar. Even though this is a state machine, it's done wrong. Do you really need to expand your parsing of every character that way? I mean, what does that tell you about what is it that you are parsing? And also notice, this is 2,000 lines of code for HTTP parse, right? So in fact, that state machine for parsing HTTP headers has 57 switch statements, 272 single character case clauses, and over 2,400 lines of code. It's unintelligible. It is a state machine, but it is a state machine done wrong again. It has nothing to do with the specification of the language. It doesn't start with the grammar. You cannot glean the grammar of what you're parsing from that. So you should be using a different way of constructing that automaton. Parser combinator style. When you combine simple combinators for your terms and your productions, and the structure of the language visible would not have, I bet you, would not have had 10 years in the running before it was actually found out that exactly the same bug that Apache had in 2002 existed in it. So here we go again, right? Look under your feet. So what does the future hold? It holds a hammer. This is the Hammer project by upstanding hackers, Meredith Wave. And this is a parser combinator style for parsers in C or in any other language that you care to write in which the structure of the code is trivially similar to the grammar. Of course, you have to come up with the grammar first, but then when you have, you can actually glean the grammar back from the code. And this is the most important thing, because that code you can actually audit. And other kind of code, good luck. And Tongs is a work in progress. This is a Hammer implementation of standard algorithms, so standard protocols. And we hope to have that released sometime next year, right? Yeah, so in 2014, this year, we had a LangSec workshop. We should cycle through this again, where you could exchange notes with other attendees and listen to paper presentations and research reports on how to do that kind of input processing right. We are going to have one this year as well. We should let's cycle this once again. I absolutely love those banners. Felix donated them to the great cause. And I invite you to join the conspiracy. It's a time to stop producing poor parsers. It's time to stop trusting in poor parsers. When we know the way input handling should be going, why isn't it going this way? Why do we keep recommending solutions that are known to not implement it? You know, OpenSSL, state machines, HTTP encodings. What is so hard about all that? It stops being hard once you accept the proper model. And I recommend the LangSec conspiracy to you. It might save your product. It might save your customers it might save your private data. Thank you.
Yeah, do you see that you get people starting to use LangSec as best practices or best coding guidelines or stuff like that? Is that starting to appear more?
We have been asked by various people what should they do on a number of occasions, yeah. And we provided our answers, right? It will take quite a lot of time and hammer and tongs and a whole lot of other tools to get this ubiquitously in production, obviously. But I would say that the attention is there. For example, Dan Geer, who is very respected in the InfoSec community, has talked about LangSec as the right and proper practice in several of his keynotes, including his Black Hat keynote. So we hope that people will start paying attention. Because, you know, we've gone through those really simple bugs today, and yes, hindsight is 20/20. However, it should not have been hindsight. None of those insights are all that hard, and there is really nothing much that was required in a software engineering environment to do it right. And of course, now that it's done wrong, it will take quite a bit of time to replace, and we'll keep running into parser differentials and all that kind of thing. But this is, I mean, what other hope do we have other than doing things right, other than doing things properly? You know, if input carries away your computation, if input elopes with your computing power, you have no other way than to deny it properly. For that, you need to understand it. You need to model how that elopement happens. And then you have to construct your communication boundary code according to that model. And the model is whatever consumes text is essentially an execution environment for that text as a program. So now you need to know what that execution environment is, what the language of that program is, and how to contain it. And again, we know how to do that. We have a classification of languages. We have a classification of automata. This is taught in Programming 101 and is then promptly forgotten because it doesn't apply to reality. Well, we have to make it apply to reality. In fact, yeah. Yeah. In fact, what happened after Lennon Meredith gave a talk at Dartmouth about how formal language theory, those very boring automata, very boring and abstract automata, and very simple ones too, that were taught in the theory courses, how they actually blow up code if they're not implemented right. Students came up to me and said, wow, I never realized that theory actually had anything to do with parsing. I'm like, facepalm. But yeah, and it was quite a few students who told me that this saved the theory course for them by providing relevance. And this is science, right? Computation is a matter of science. There is, I mean, this is the reason why Turing and Church and other mathematicians who do that sort of thing, why they are counted among, you know, mathematicians in so much as mathematics is science. If you do it wrong, then it runs away from you and it blows up your product. And that's just it. It's not simple. I mean, it is simple once you have the theory. But good intention, as with any kind of science, as with any kind of learning, good intentions don't get you there, right? The reason, and you know, just trying hard doesn't get you there. Science does. Specific, precise knowledge does.
So maybe you should try to get the whole LangSec thing into common criteria or something like that too.
Felix has had some success getting it into purchasing requirements.
Awesome. Awesome.
I recommend our talk, our invited talk at Usenix. It was called Information Security War Room. And we talked about what to do about things in the real world where legislation happens and purchasing happens and standards happen. And besides, you have large deployed bases. So the slides are online at Usenix Security. That was our invited talk with Felix. So Information Security War Room, you can download the slides. And
awesome.
Hopefully video will be online at some point as well.
Awesome. Questions from the audience? No? You're all that hungry. All right.
I will have you note that I was on time.
You are on time. You're very good on time. It's 5 minutes. Thank you very much.